Classical free electron theory, a fundamental concept in solid-state physics, helps to explain the behavior of electrons in metallic substances. This theory is built on several key assumptions about electrons, their interactions, and how they conduct electricity in metals. One of the primary assumptions is that electrons in a metal can be modeled as free, non-interacting particles, much like a gas. The theory posits that these electrons do not experience any potential barriers due to the atomic lattice of the metal, which simplifies the analysis of their motion and energy distribution. This perspective allows scientists to use statistical mechanics to describe electric conductivity and thermal properties without the complexities of electron-atom interactions. Another critical assumption of classical free electron theory is that metals contain a significant number of free electrons. In a typical metal, some outer shell electrons can be loosely bound to their corresponding atoms. These electrons can move relatively freely when an electric field is applied, contributing to electrical conductivity. According to this theory, the density of these free electrons is crucial. Higher densities typically lead to better conductivity. Thus, metals like copper and silver, which have a high density of free electrons, exhibit excellent electrical conduction. The theory also assumes that these free electrons obey classical mechanics, rather than quantum mechanics. This assumption means that their behavior can be described using classical equations of motion, such as Newton's laws. However, it is important to note that this classical approach fails to account for quantum effects observed at smaller scales, particularly in materials that exhibit significant deviations from classical behavior. Despite this limitation, the model can adequately describe many properties of metals at normal temperatures and conditions. Additionally, classical free electron theory assumes that electron collisions are perfectly elastic. When electrons collide with impurities, defects, or phonons, they do so without losing any energy. They merely change their direction. This assumption is key in simplifying calculations regarding the scattering of electrons as they move through the metal. However, in reality, inelastic collisions do occur, leading to energy loss which can affect overall electrical resistance. Nevertheless, the assumption of perfectly elastic collisions allows for a more straightforward analysis of conductivity and serves as a useful approximation in many scenarios. The theory also holds that the thermal and electrical conductivities of metals are primarily determined by the movement of these free electrons. Increased temperature typically leads to an increase in the lattice vibrations of the metal's atoms, which can impede the motion of the free electrons. However, the theory asserts that as temperature rises, the number of thermally excited electrons increases, balancing the conductivity to some extent. This interplay between temperature and conductivity is an essential consideration in the application of the theory to real-world scenarios. Classical free electron theory has led to the development of important equations in solid-state physics, such as the Drude model, which quantifies the relationship between the mobility of electrons and the applied electric field. This model describes the current density as proportional to the electric field and the electron mobility, providing a mathematical foundation for understanding electrical conduction in metals. The mobility of electrons, a critical factor in this equation, is influenced by the scattering mechanisms discussed earlier, including collisions with lattice vibrations and impurities. While classical free electron theory provides valuable insights into the electrical and thermal properties of metals, it is essential to recognize its limitations. For instance, it does not accurately account for phenomena in superconductors, semiconductors, or insulators, where electrons behave more like waves than particles. Furthermore, as technology advances and materials science evolves, the need for a comprehensive understanding of electron behavior necessitates the exploration of quantum mechanics and models that extend beyond classical assumptions. In summary, classical free electron theory serves as a foundational framework for understanding the behavior of electrons in metals. By assuming that electrons are free, non-interacting particles that obey classical mechanics, the theory simplifies the complexities of electron dynamics. Although it falls short in certain areas, particularly in explaining quantum phenomena, it remains a crucial tool in physics for analyzing electrical and thermal conductivity, allowing researchers to make significant strides in the field of solid-state physics.